So, on Tuesday, we talked about something a little obscure called a Riemann sum, and how it's, come on in, find a chair. May I suggest you grab a chair from there and put it here, because you'll get a better view. If you don't care about the view, you can sit off in the wings. We talked about how Riemann sums are used to define something called a Riemann integral. And we're not going to call it a Riemann integral anymore. We're going to call it an integral, or more specifically, a definite integral. And as we saw, a definite integral, we use this notation, this kind of curly sign, which is supposed to represent a big S. Gives the idea of the word sum. Right? Sum. And we give it limits. Right now I'm just going to be using constants A and B. Some function of some variable, and this we've only used x till now, and then we say dx, indicating x is the variable that we're going to integrate along, typically the x-axis. This is what we call a dummy variable. If I was to write this as f of t dt, because I want to make you think I'm integrating in time, it's exactly the same. The dummy variable doesn't matter at all. And it's very important to note that a definite integral is a number. Now, we're going to talk about definite integrals today. But before I do, I want to give you a little look ahead, because this notation is used in other ways, slightly different. For example, instead of writing it this way, I could just write it without the A or the B. I could just say integral of f of x dx. And what I mean by this is basically almost exactly the same thing you think of when you think of an antiderivative. So if I said, what is the, I guess I should give this a name. This is an indefinite integral. If I said, what is the indefinite integral of 2x? X squared, and I heard that other part, and I'm going to go there in just a minute. But certainly, you should know that the derivative of x squared is 2x. So this is a correct statement. It's correct, but it's incomplete. If this was always true, then I could say that an indefinite integral is a function. Really, x squared is a function. But that would be almost true, but not precisely true. The reason is that while the derivative of x squared is certainly 2x, so is the derivative of x squared plus, let's say, 5. Right? Derivative of the sum is the sum of the derivatives. The derivative of a constant is 0. So the way we indicate that, we usually, when we have an indefinite integral, we'll say x squared plus c, as someone pointed out. C being some number, unknown. So an indefinite integral is not a function. It's a family, that's the word we use, of functions. They all get along, right? On Thanksgiving. Just think of all the possible C's you could put here. All those functions make a family, and that's what an indefinite integral is. Okay. There's one more use we're going to see. And it's not very different. We're going to see it today. I could write can everybody can't see over this. That's a good idea. Let's see. Is that better? Okay. I don't think people can see down this low, can they? All right, cool. I think we should just get a new room every day, right? So I can, have to mess around with them quickly here, right? Okay, so the third possibility is we might see something, let me write it this way. Now, what do I mean by this? Well, the definite integral, what I mean is I have some function, and I want to integrate from point A to point B. And so, there's some area in here, and it's a number. I mean almost exactly the same thing here, except it turns out different. What I mean is, I'm going to integrate from A to some point X. Oh, this is very bad what I just did. Because I can't have X here and here. That would be confusing. So I'm going to instead have a T axis here. And now, what I have is a function, an area function, which says, what is the area from A to some X I give it? It's a very subtle difference, and if it's a little confusing right now, that's okay. This is the third usage of the integral sign here. So this is number one, definite integral, indefinite integral, and then here we have a function. This most definitely is a function. Just like all the other functions you've studied. Okay. Are there any questions about this yet? Okay. I did want to make a side note about the indefinite integral before I go on. Yesterday we were looking at the fact that if I have, it's going to make up a, well, let's not make up a problem. I'm going to use the problem I used in my notes. I have an integral from 0 to 1, 3x squared dx. And I suggested yesterday that we might solve this by finding the antiderivative, which is x cubed, and putting it in this notation, which means we take 1 cubed minus 0 cubed. Now, just a minute ago we talked about the fact that when you take the antiderivative, certainly when you take the antiderivative of an indefinite integral, you don't just get x cubed. You get x cubed plus c. And I just wanted to point out that in this case, if I evaluate it the same way, I get 1 plus c minus 0 plus c, which just comes out to be 1. The c drops out. So I just wanted to make that clear. When you're dealing with an indefinite integral, you get this constant of integration. But if you actually then go to apply to make it a definite integral, that constant disappears. I think I have a few minutes to waste to do some fun facts, right? People like fun facts. I know you've all heard of Albert Einstein. Most of you have heard of his theory of general relativity. And in coming up with the fundamental equation of his general theory, he does an integration, and he got a constant of integration. And initially he didn't know what to do with it. This constant is called the cosmological constant. Has anyone heard of this? No? Okay. Whenever they go in and out of the door next door, this happens. I'm going to try and do something about that. Actually, I'm going to try and do something right now. I don't think it'll work, but I'm going to lock this door and see if that doesn't diminish the noise. Next time you come here, do come in, even though we're supposed to be in 5502, come in this door. I'll leave that one alone. So, that was okay. He came up with his theory of gravity. And then a few years later, someone tried to apply it to the universe. Universe, we look out, we see galaxies far away, and we know gravity pulls them together. And Einstein thought, well, the universe really looks static. So how can it be static if gravity is pulling it together? He thought, oh, this C is just a repulsive force, keeping everything far apart. And a few years after that, an astronomer named Edwin Hubble discovered that actually the universe isn't static. All the galaxies are moving away, the universe is expanding. I'm sure you've all heard this. And Einstein, in regret, said, you know, this is the worst mistake I've ever made. Right? That was his response. Well, Einstein died in, I think, 1955. And so he didn't get the good news, which was about 10, 12 years ago. was discovered that not only is the universe expanding, but gravity is slowing it down. Despite that, things are moving away faster and faster and faster. There's actually a repulsive force of some kind pushing things away. Anyone know what that's called today? They have a name for it. You've heard it if you watch television at all.
Big Bang Theory.
Speak up loud.
Big Bang Theory.
No. The Big Bang Theory is that the universe is expanding. That's important. But the fact that not only is it expanding, in the Big Bang, it expanded and gravity would slow it down, and maybe it would come together, or maybe it would keep going, but it would keep slowing down. It's actually moving away faster and faster over time. This was discovered only about 12 years ago. And it's called, what they call it, mysteriously, is dark energy. Anyone heard of dark energy? So, I just thought constants of integration, they're just kind of mathematical things that pop up. But it looks like, because we don't know yet, that this constant that popped up in Einstein's equation actually has some real meaning. Okay. I'm sure you'd all rather hear me talk about astronomy all night, but we can do it now. Okay. So let's get back to this really important idea. I just don't know what to do with this yet.
Professor?
Yes?
Maybe you just open the door a little bit. Maybe 2 rooms are in.
I can do that, and then it will get cold.
A little bit. Just,
You think that's, everyone agree? Okay. See, one of the things here too, we're in math and maybe some science or engineering or whatever, but why do we want to engineer? To solve problems? Well, let's still get a bang next door, but our door isn't going to bang, you see. I have a solution. I'm going to have to talk to the teacher. You're going to have to entertain yourselves for about a minute.
可以直接写后面的，这是自己想的写，因为最后加上去，跟以后算你这样关去过，就他家里可能也去过，在你那
Okay, where was I? We're looking into this possibility that if we have some integral that if we can find a function, an antiderivative, such that the derivative of this function is f of x, then this integral can be computed as f of b minus f of a. That would be really nice, because that would reduce our problem of computing integrals to finding antiderivatives in most cases. So the question is this true? And if it is, if it is true, how can we show it's true? So here again, we have one of those places in the class where I'm going to show you something. Some of you, when this is over, are going to go, wow, incredible. And some of you are going to scratch your head and go, I didn't quite get that. But it won't matter, because you'll still be able to use this important fact. I guess I don't understand the geometry here quite right. Okay, so to show this, I'm going to start off by defining a function using an integral, the way I demonstrated, the third way we can do this. I'm going to call my function f of x, and I'm going to define it as the integral from some constant a to x of f of t dt. Now, I want to draw you a picture of what that looks like. So I have some function, f of x, and I'm defining this capital F function as the area between little a and x. Okay? Now we're going to jump right back into last semester, and I'm going to show you something that might look familiar. I'm going to look at the limit as h approaches 0 of f of x plus h minus f of x over h. Now, those of you who already have a feeling for this, great. But if you don't, what does this kind of smell like a little here? Definition of derivative. It looks a little like, all right? All right. So before I go forward, though, with what this is, by the way, this is not a proof. Everybody know? Everyone took geometry, so everyone knows what a proof is. I'm hand waving here. If you want to see the proof of this, you got to hang around for a few more math classes. But I do want to try and convince you this. So now let's take a look at my function. Here is a. Here is x. Here is x plus h. Okay. And then this here has to be f of x. And this distance here, I thought I saw that. Just doing it now. Their door is supposed to be locked. They're not. Maybe someone left through that door. Okay. So now, this is f of x, and this is f of x plus h. So what is this? F of x plus h. Big X, big F, x plus h. That's the area from A to x plus h. I'm just going to draw a line here. Area of, from, every year I have to relearn that my finger is not a good eraser. Area from A to f of x. All right, not very good notation. What is f of x? Well, it's the area under this curve from here to here. So this difference here, I guess I can write this now. This difference is just this area in this section here. Everybody see that? Pretty straightforward. And of course this little piece down here, that's just length little h. Okay, so if I divide this, if I divide this area by h, what do I get? Approximately. Like if this was, h was very small and this was a rectangle. Or actually, if this was a straight line and this was a trapezoid. Right? Well, if I divide this by h, that's just the average of these two. That's f of x plus f of little f plus h over 2. That's the average height. I'm doing something wrong, but I'll fix it before I go forward. Oh, times h. Right? Is that right? Put my limit back in here. This area is this. So if I divide it by h, I just get the average height, which is just what I said. F of x plus f of plus h over 2. Yeah, that's it. That's it. So, what's the limit as h approaches 0 of f of x plus f of x plus h over 2? To evaluate that limit.
fx.
That's just f of x. But as was pointed out, this is a definition of the derivative of big F of x. I'm going to cheat here. Okay, so let's go back and look at this. I have some function. It gives me, it's an area function. Right? And I know that the derivative of this function is exactly the function I'm integrating over. And that's what I wanted to show. a little too transparent for even me to pick up on. This tells me that our strategy is going to work. It's going to work at least if this limit exists. So, okay. We're going to talk about this some more next week. This is part of what's called the fundamental theorem of calculus. It's fundamental because it connects derivatives and integrals. Okay. Any questions on this? I feel like I'm talking too much and I should have more pictures, but we'll get to the pictures. Okay. It was pointed out to me, well, before I say that, so finding antiderivatives, you can see, is going to be really important part of this class. And the easiest way to find an antiderivative is to already know it. Okay. Let me show you what I mean by that. Let's start out with something real basic. Derivative of x to the n. Who can tell me what that is?
10 times x to the n is y.
Okay. So now, if I wanted to find the integral of n times x to the n minus 1 dx, that would be
x to the n
plus, we'll be a little pedantic here and put in the c's. But this isn't the nicest way to put this, because we're not always going to get n in front of x to the n minus 1. So it might be nice to realize that since n is just some constant number, that this will just be x to the n over n. And, why should I deal with n minus 1? Let's just replace this. Let's just add 1 to the n's. All right? This becomes n plus 1 over n plus 1. Okay, so now, because we know an integral, a derivative, we now know an antiderivative. Okay, so we can make a lot of hay with that. All right? So let's give this a shot. The derivative of e to the x is
e to the x.
The x. So the integral of e to the x dx must be
e to the x
e to the x plus c. Now, we can get a little fancier here. We could say, what's the derivative of e to the ax? That's, of course, a e to the ax. So we get a factor of a in there. If we go and look at the integral, now we have to divide by that a. All right? Okay.
It's e to the ax divided by
ax, thank you. I appreciate you keeping me completely honest at all times. Okay, I think we even talked about sines and cosines last time. How about this? Derivative of 1 over x. Wait, am I going to do this right? No. Yeah, derivative of 1 over x.
1 over x squared. 1 over x.
Yeah, I thought that wasn't the one I wanted. Oh, thank you. What's the derivative of the natural log of x?
1 over x.
That's 1 over x. Okay. So the integral of 1 over x is?
Absolute value of absolute value of the natural log of x.
Okay.
No, it's inside of the, I think inside of the x.
Yes. So we have a student here who's a little ahead of the game. This is an important reason we put this, the absolute value, because the log of a minus of negative number isn't defined. At least it's not defined in the real number line. Okay. I'm just going to put these down. Derivative of sine of x is the cosine of x. So the integral of the cosine of x is just the sine of x. Let's see, similarly with the cosine, what's the derivative of the tangent? Now we have to dig deep into our first order knowledge. Have a cheat sheet? I'm fine with cheat sheets. Anyone remember derivative of tangent of x? Well, if you're ever stuck on an exam and you don't have your cheat sheet, you don't have your 96 calculator, just remember that the tangent of x is the sine of x and the cosine of x. And we do have a formula, don't we, for a fraction like this? How does that go? It's the sine of x times the derivative of the cosine of x minus the cosine of x times the derivative sine of x all over the cosine squared of x. And this turns into 1, so it's 1 over the cosine of x, so it's the secant squared of x. Okay, so now I know, I don't expect this to come up quite as often, but whenever I want to find the integral of the secant squared of x, I can get tangent of x. Okay. Now, that's the easy stuff. I want to get into something a little bit harder. I just want you to be aware you're going to need to know this. So if you don't know it, maybe you should review it. Wonderful eraser. Back in the dark ages, when dinosaurs roamed the earth, and I was in college, I had a professor, I guess he'd been at it a long time, and he would sit there like this. He would write with one hand and erase with another. It was amazing. Maybe after another 20 years I can do that. Okay, so everyone remember what the arc sine or inverse sine of x is? The inverse function of the sine. And we do know what the derivative of that is, don't we? In the last class, we were using the Stewart book. And the Stewart book has in the back a little pull-out thing with tables and derivatives. And I don't mind if you have a sheet like this for tests and quizzes, because when it comes up, it's really handy. So this is the square root of 1 minus 1 minus x squared. And I think the cosine is the same thing with a negative sign. And you should know that this does come up a lot. This is really important. Anyone remember what the derivative of the inverse tangent is? Very good. Okay, so this of course gives us some new integrals. Sine inverse of x. And I'm going to leave off the cosine, inverse 1 over x squared tangent. One of the techniques we're going to use later on to deal with finding the integral of rational functions breaks down a rational function into, you might have like a over x plus b over x cubed plus c over 1 plus x squared. This comes up pretty commonly, so this is a good one to remember. Not tonight, but because when you're doing this technique, you get something in this form and you have to find its integral and blah, blah, blah. Okay. The only other thing I'm going to mention, I don't think they cover it here. They don't cover the hyperbolic functions, but there's a set of functions similar to the sine and cosine and the tangent in some ways. They have the same relationship to a hyperbola as these functions have to a circle. And they're defined, hyperbolic sine is e to the x minus e to the minus x over 2. Hyperbolic cosine is e to the x plus e to the minus x over 2. They're not periodic functions. They kind of go off into infinity. But they have this very interesting property, which you can demonstrate for yourself with your knowledge of calculus, which is the derivative of the hyperbolic sine of x is the hyperbolic cosine of x, and the derivative of the hyperbolic cosine of x is the hyperbolic sine of x, which means that the integral of the hyperbolic sine of x is the hyperbolic cosine of x plus a constant, and likewise the hyperbolic cosine of x, the integral of the hyperbolic cosine of x. I'm getting sloppy here. I'm leaving off the dx. We often do that. It's okay. As long as you know what the dx is, it's okay. Hyperbolic sine of x. And this will come in really handy much later in the course when we look at a very ugly animal called differential equation. Differential equations, a lot of the technique for solving them has to do with this wonderful property or its equivalent integral property. If I have some function and I say f of x equals a times the derivative of x, it's really good to know some function that doesn't change much when you find its derivative. And if you're unfortunate enough that it's a second derivative, this can come in handy because you find the derivative twice and you're back where you started. Okay, a little prequel. A little early, but I think we're going to take a break for 10 minutes. And then people can come up with their various administrative issues like add codes. Anyone who needs an add code, please step forward. If you want to use the app, that's fine. I think it's a good idea since these, they may go away in a few years, but they're still around. I think you should know how to use one of these. And when it comes to a test or quiz, I have 3 myself that I will loan people. So if there's more than 3 who have the app, and then we'll have to figure out what to do. I might be able to borrow some for tests and quizzes. It's merely, this isn't my choice about it at all. I'm just a part-timer here, and I have to follow the rules too. So that's the story. For now, use the app, and I will find out before the first quiz what the story is and let you know. Okay. We ready? Any other questions? This is not going to end well. All right. I just want to do 1 or 2 more basic problems, and then we're gonna look at some more features of the definite integral. Okay. You're welcome, if you have some paper, to follow along. Let's take a look at just a very simple problem. I want to find the definite integral from 2 to 4 of x squared dx. We've already done parts of this. Okay. So, anyone want to give me a hint on the first step? No one was listening to the first half of the class? What do I want to do with x squared?
Find the antiderivative.
The antiderivative, yeah. So the antiderivative of x squared is x. So what do I do? So when I'm finding the derivative, I subtract 1 from this number, right? So when I find the antiderivative, I add 1. Then I have to divide by that number. Now, I've been using this notation, which is very common. I'm just going to introduce you now to a slight variant that you will see, which is, we just put it in brackets, but it's the same meaning. I want to evaluate this, so I evaluate it at 4 first. X cubed, 4 cubed is 64. Then I subtract the antiderivative at the other limit. So that's 8 thirds. So I get d6/3. And I know that's in lowest terms, right? If you write this, I will be very sad. If you write this, I will frown but mark it correct. Right? Does everyone understand? I like this. I used to teach high school. Freshmen in algebra, I would tell them, fractions are your friend. But in any event, okay. What have we just done here? Well, the graph of x squared kind of looks like this. So if we, this is not to scale, but you believe this is 2 and this is 4, I just found the area here. You know, I've been doing this a long time, and I feel like the excitement of suddenly, you know, going from geometry where we could find the area of a circle or a rectangle, to suddenly now we can find the area of almost anything we can have a function. It's, you know, I've lost that excitement. I hope you have a little of that excitement in you. Let's take a look at another. I guess I'll do this here. Again, I want to find the integral of the cosine of x between pi over 3 and pi over 2. Maybe you'll do the I'll do the graph first. So cosine kind of looks like this, right? And this would be pi. 2 pi would be where it becomes periodic again. So between pi over 3, that would be kind of over here. And pi over 2, that would be right here. Okay, so this area I'm trying to look for. Okay. So again, now I want to find the antiderivative. What did we define? What did we decide the antiderivative of the cosine was? This is something where you just kind of work it backwards and figure it out. So, well, what's the derivative of the cosine? That's not really what I want. That's the negative sign. No, okay. Derivative of the sine, that's the cosine. So the antiderivative of the cosine, that's the sine. Okay, pi over 3, pi over 2. Okay, and the sine of pi over 2. 1 minus the sine of pi over 3.
Here's 3 over 2.
Figure that out. I have to go back and look at my trigonometry. Pi over 3, that's 60 degrees, right? And the sine, that's the opposite over the hypotenuse, right? That's the square root of 3 over 2. That sounds right? So it's 2 minus the square root of 3 over 2. Now, I know I'm repeating myself. I remember in English class, when we were studying literature, the teacher said, the author ever repeats themselves, it's important. So if you tell me the answer is I will cry. But unless I told you use the calculator to figure it out, I won't mark it correct. Okay? All right. All right. One more problem for fun. How can you have as much fun as you have when you're doing this? I'm going to change the problem I have here a little. Just a little. So I want the integral from 0 to 2 of e to the pi x dx. So let's see, what does that look like? Exponential, right? And it looks like this. And I want to find the integral from here, 0 to, again, from the scale. Okay. So I know what the antiderivative of e to the x is, right? E to the x. So the derivative, the antiderivative of e to the pi x is probably going to look like that. So as my first guess, I could just try that. And then say, well, okay, what's the derivative of this? Well, the derivative of e to the pi x is e to the pi x times pi. And we know that because of the blank rule. Blank rule? Let's fill in the blank. I want to fill in the blank. Chain rule? Chain rule? Right? In other words, e to the pi x is e to the pi x times the derivative of pi x, which is pi. Okay. So I know if I find the derivative of this, I get this, but that's not what I want. I want this. So it would help if I start off with e to the pi x over pi. Now when I find the derivative, it's going to come out right. Okay? Okay, so now I just have to plug in. So I have e to the 2 pi. Let's put this down here. Minus e to the pi times 0, which is
1.
Okay, good.
1 over pi.
Well, I drew a big line here to get it all over.
Okay. Yeah.
You could do this. Right? It's a constant. We're going to talk about this in a minute, a little bit more, but you're going to find, just like with derivatives, constants move in and out of the derivative sign without a problem. They're going to move in and out of the integral without a problem. So if I said 2e to the pi x, I could just move it out here and everything would be fine. Okay. All right. there's some, we've really got the basics here, but there's some pieces missing. So, let me show you an example. I had f of x equals, say, minus x. I want to find the integral from 0 to 1. F of x dx. Let's draw a picture of that. So there's my f of x. There's 0 and there's 1. So up till now, we've been looking at the area under a curve. Under the curve and above the x-axis. So what do we do with this now? Well, let's go ahead and just play this game we've been. Let's figure this out. Okay. So I guess I'll want that back again. So what is the integral of negative x? It's the antiderivative. Well, if it was just x, it would be x squared over 2, right? Since it's negative x, it has to be negative x squared over 2. 0 to 1. Okay. So this is negative 1/2 minus 0. It's negative 1/2. Now I really want that diagram back here. Clearly, this is not the area. Draw something better. It's not that area. Why is it not that area?
Cannot be negative.
There's no such thing as a negative area. But this is the way integrals work. This actually is the negative of that area under the curve. Right? If you go back to our original definition of the integral, it has to do with Riemann sums. If f of x is negative, this sum, the delta x's are positive, it's going to be negative. So the pearl of wisdom here is that integrals are not just area in the geometric sense. It's not always positive. You can have, area below the axis counts as negative. And in fact, if I change this just a little, say let's go from negative 1 to 1, right? So now we have a component that's above the line and a component below the line. What's going to happen now? Well, negative 1 squared is 1. So negative 1/2. So negative minus a negative 1/2, which is, of course, plus a positive 1/2 is 0. So here we have an integral. There's clearly stuff, above the line and below the line, but they cancel.
Is this a vector word? Can we say a vector word? No.
Louder.
Can we say what the integral does can make a value be the vector or something?
It's the last word I'm not hearing.
A vector.
A factor?
Vector.
Vector.
No.
Oh, a vector. No, it's a number.
It's a number.
Remember, definite integral is a number. Zero-dimensional vector, but that's too technical.
Okay.
It's not a vector. No. A vector has direction. This merely has magnitude. I'm sorry, the reason I didn't understand what you're saying was because of the context.
Oh.
You see, I could partially hear it. If we were doing linear algebra and you said vector, I'd know what you were doing. My apologies. I'll get better at it. Okay, so something to be aware of is that below the line, we're kind of adding negative area, if you like. It's just something we just made up. And if the function goes up and down, it's the net value. Okay, so that's important. Okay. Again, there's a few more pieces we need here before we're proficient at this. Next thing I want you to look at is how we can manipulate an integral in ways that are useful to us in trying to calculate it. So, again, this is not a proof, but this is a hand wave, but I think it'll be very clear. So let's say I have some function, and we'll call this section here area 1, and this area 2. So clearly, area 1 plus area 2 is the integral from a to b, a to c, of x. But a1 is just the integral from a to b of f of x. And area 2 is just the integral from b to c of f of x dx. So I want you to look at this real closely. I can take an integral between certain limits and I can break it up into pieces. In other words, instead of going from a to c, I can go from a to b and then b to c. And I could break it up into many pieces. This is really useful if you have a piecewise defined function. Does anyone remember what a piecewise defined function is? Okay, f of x equals 1 if x is less than 0. X if x is greater than or equal to 0 but less than 5. And x is 3 if x is greater than or equal to 5. So I want to find the integral of f of x from, say, -2 to 10. How am I going to do this? Well, clearly this tells me where to break it up. Right? It's the integral from -2 to 0 of f of x plus the integral from 0 to 5 of f of x plus the integral from 5 to 10 of f of x dx. Now, I'm not going to rewrite this. I'm just going to cheat and say, well, from -2 to 0, 1. From 0 to 5 is x. And from 5 to 10 is 3. And now I just have 3 simple integrals to solve to compute this. Okay. Everybody happy with this? Okay. Now I'm going to do something a little tricky with that little formula we had over there. See if I can get away with this. I didn't change my formula. I think my formula, well, I have to remove this. I didn't change my formula. I just rearranged these points. But this should still hold. I have to think about what does that mean. Well, the integral from A to C, that's area A1, equals the area, the integral A to B, that's A1 plus A2. This is the integral from B to C. And note, this is the first time I've written this integral where we've been going left to right. But this is right to left. So I'm not sure what this is.